Hi, boys and girls. The instructor here, yet again. Let's talk for a few minutes about waves. We've been talking about the disturbances known as waves. A wave is a disturbance that moves through either a substance or empty space. We categorize waves in a couple of different ways. The first way is, does it go through a substance? Does it have to go through a medium is the word? A medium is just the material that a wave can go through or will go through. Some waves require a medium. We call those mechanical waves if they have to go through a substance. The other kinds of waves would be electromagnetic. They do not require a medium. They're the only kind of waves that can go through empty space. Electromagnetic waves or light waves. Okay? Now you guys being so brilliant, you should be able to just follow right along in your notes because this is stuff we've talked about, right? And your notes are out because you and I know if I'm up talking, you're writing, or we're not doing our job. So if I do my job and you don't do your job, only 50% of us did our part. Not good. Now the other way we classify a wave would be how it moves. We talked about how light waves move. And we called, well, it was the T word. What kind of wave are light waves? They are transverse. And we demonstrated a transverse wave with a slinky, didn't we? Remember that one? Yeah. That was a great lesson. Okay? Did you see the next, well, you didn't see the next guy. We call the next type of wave longitudinal when we talk about how the wave moves. A longitudinal wave moves, well, let's just review a little bit. This Calderon, right, is my faithful assistant. She will hold that in. And this is the longitudinal wave. It is a play written by C.A. Cunningham I. So the origin of the wave will be here because I'm going to create the disturbance. Oh, beautiful. Watch again. That's a longitudinal wave. Where'd the energy go? What direction did the energy go? From my hand to where? Her hand. Which way did the medium or the slinky go? Did it go up and down? Where'd it go? This way. Same direction as the energy, didn't it? Except it went back and forth, didn't it? We call that a longitudinal wave. So what happens is when you talk about the energy, okay, of the wave goes that way, it went back and forth, but the medium, which is the substance, the atoms, the molecules of the material went the same direction, didn't they? So it's moving parallel to the medium. That is a longitudinal wave, when the energy and the medium are moving parallel to one another. You guys with me? I know what you're thinking. Mr. Cunningham, what's an example of a longitudinal wave? Sound wave would be an example. It's the most classic example of a longitudinal wave, a sound wave. Okay? Sound waves start from a point of origin, and they dissipate, they move outward in all directions. Okay? Sound, and don't think of, okay, but it's doing this in all directions. Okay? It's not just going that way. Can't you hear my voice over there? And over there? And over there? Sound waves move in all directions away from the object, just like light waves, but that's how they move. Okay, so a sound wave has to go through a substance. And the substance that it's going through will determine how fast it's going. Write that down. The substance that sound waves is going through, or any wave, will determine how fast it's going. So like The most common medium for a sound wave would be what? What is my voice going through right now? The chicken? What?
Mass.
What?
Mass.
What mass? Oh, mask. I thought he said mass. It's going through the mass. Then after the mass, then what? Air. Did you write down the medium determines the speed? That's for any wave. Okay, so a wave will change its speed based on what it's going through. So in air, which is the most common medium for sound, I have to pull up the number in my brain. 340 meters per second is the speed of sound in air. Okay? That's pretty fast, isn't it? Think about, how can I say it? About 3.5 football fields. I want to give you a reference point. About 3.5 football fields in a second is how fast sound waves move. Is that pretty fast? Kind of, yeah. Yeah. Yes?
Is it faster than the speed of light?
That's a good question. What's your name?
Bernardo.
Get Bernardo a bonus point quickly. There you go. So Bernardo, did I say it right?
Yeah, you said it. It's called me Bernardo.
Bernie. That's better. I like Bernie. I don't want to mix people's names up, and I'm terrible with names. That's my one flaw. And I'm moody in the morning. That's my other flaw. I got 2 flaws. Okay, so how can I say it? So the speed of light is 3 times 10 to the 8th meters per second, and that's an empty space. Empty space. If we're like through air, it's going to slow down just a little bit. It'll be like 2.9 times 10 to the 8th meters per second in air. So, you feel what I'm saying? Take this decimal, move it 8 places to the right. That's a lot faster than that. They're not even close to comparable. Speed of light is very, 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 I mean, we can't even imagine how fast. Okay? That was a good question. Okay, so the medium that the substance is going to will affect the speed of the wave. And that's really what I want you to know. I don't care that you memorize numbers. Who gives a rat's crack? You can Google the number, right? But I do want you to know that the substance that the wave is going through will affect the speed. It's going to have different speeds based on what it's going through. Many years ago, when I would say like it would be post-Civil War. You guys are in history, right? Are you U.S. history as a freshman? What are you in? What class?
U.S. history.
That's what I just said. Somebody said no. So you're U.S. history. So think post-Civil War. Give me a year. You guys are good. You know your crap. Give me a year. Post-Civil War. Quick.
When was the Civil War?
Oh, God.
We have Google 30.
Just think 1865-ish, a little after that. Okay, so that's when,
1861.
right, but 1865, that's when slaves were free, right? That was the emancipation, right? If I recall correctly. So after that, right, and the Civil War lasted up until around that time. So after that, that's when you get into, you ever heard of like Jesse James? Anybody, you watch Western movies? Anybody heard of Jesse James? Nobody. One person.
Oh my gosh.
I'm done. We don't have any reference points, guys. I really can't teach you anything because you don't watch anything, you don't read anything. So Jesse James, right after the Civil War, people like him, they robbed banks, they robbed stagecoaches, they robbed trains.
He was a famous outlaw.
Yes.
In the Wild West.
And he became an outlaw because of the Civil War. When the Civil War happened, the South, their prosperity dwindled. Okay, they used to get free labor, so they obviously had a lot of money. Well, when the Civil War happened, no more free labor. People are upset. The North ruined it all for us. We were rich. Now a lot of us are poor. We got to work for a living. This is bullcrap. So I'll tell you what I'll do. I'll rob banks. It'll be the Northerners' money that we'll steal. So they would rob trains, stagecoaches, the whole nine. they would put their ear to the railroad track because the speed of the railroad, or the speed of the sound, they could hear the train coming for miles before they would actually hear the whistle. So they would put their ear to it, and the vibrations given off by the train would let them know that, oh, a train is going to be here soon. By the time you hear the whistle, it's too late if you're not ready with your ambush. It's too late. Okay, so that's how they would actually get in place to rob the train, because they use science. Oh, we will hear the train through the metal railroad ties before we would hear it in air. Okay? Because sound waves go faster through solids than they do in air. True story. So, my point is this. If they can deduce that, we should be able to say, you know what? All I need to know, Mr. Crime said, know that the speed of the wave is different based on the medium it's going through. Okay? That's the importance of this stuff. Okay? So sound waves do this. Okay? Compressions and rarefactions, we don't have to know that word. So like a transverse wave, we say crest trough. With the sound wave or a longitudinal wave, we have compressions and rarefactions. And if something's going really fast, okay, so the sound wave, picture like a cone, starts small, get bigger, bigger, bigger. That's how it dissipates. So the sound breaks up when it goes a long distance. Are you with me? So imagine something going fast enough where the sound wave it creates overlaps with the sound waves that are already out there that it created. So that's how like an airplane, when they fly really low, they break the sonic barrier. And if it's really low, it'll shatter windows and such. Because the plane's going so fast, the sound waves overlap to a point where there's not enough time for the waves to dissipate, and you get this boom effect. Feel free if you want, for extra credit. I don't know if you guys like extra credit. You guys like extra credit?
Yes, we love extra credit.
If you like extra credit, you do me a 3 to 5 minute oral presentation over sonic barrier being broken, and your instructor will get you 3 bonus points. You with me? Write that down. All right, so that's an example of longitudinal wave. Any questions? So longitudinal wave, energy's that way. The medium's same thing. So it's parallel to one another. Example of a longitudinal wave is a sound wave. Okay, the sound wave will go about 341 meters per second in air, but as it goes through different stuff, its speed will change. Okay? Preguntas. You can cut the video, Ms. Fido.